Backed by fairly popular demand and some curiosity, I purchased an anemometer. This one is probably a piece of junk, but it should hopefully be good enough to develop a concept. What I want to do with this is attempt to measure CFM. And I say attempt because it'll probably fail, but we're going to give it a shot. So I have some calculations here or these are formulas rather. We know that the CFM equals area in square feet times velocity in feet per minute. So we can calculate the area using a tape measure, and then hopefully we can calculate in feet per minute the air speed with that anemometer. So we're going to start by trying to measure the CFM of this blue blower fan, because according to the product specifications, this moves 300 CFM, and it's a rectangular output, and the output should be even across the register for the most part. So I feel like this should be a pretty controlled and simple use case to start with. When it comes to a ceiling fan, it becomes a little more complicated because there is an area in the middle here which accounts for a significant portion. It's probably, 1 or 1.5 square feet where there's no airflow. And of course the airflow right here is different than it is out here. So I think for the ceiling fan, we have to kind of calculate the area of, and maybe even where the blade irons are. Does it seem like it moves? I don't know, this fan moves so little air, I feel like it doesn't even move in the air until like here. I feel like it doesn't move much air past here. But there's really little to no airflow taking place anywhere from where the blade irons are inward. So I really think that you would have to calculate the whole area of the fan and then calculate maybe from here to here and subtract that calculation from the first one, and then that's your actual surface area. And then I don't know if you would just take a measurement in the middle or maybe take 3 or 4 and average them together. I don't know. That's going to get a little bit complicated. But let's start with this blue blower, because at least we know if we do something and we get a number around 300, then I feel like whatever we're doing is kind of working. So let's open this anemometer. This was not the cheapest one I could find, but it was definitely one of the cheaper units, just because we really don't need anything all that scientific here. This is able to measure in miles per hour from 2.4 to 65. I really don't think we're going to do anything that exceeds 65. That is really quite strong. It has wind chill indication, which is kind of neat. Unfortunately, it does use a 2032 battery, which I didn't realize at the time of purchase. Chances are it probably lasts long enough that it doesn't matter, but I would have preferred something that takes a AAA cell battery so I can just drop in a rechargeable. What is this? Why does it come with a screwdriver? Is there assembly required? It'll come in a nice little protective cover here. And this is the unit itself. And I guess this is a little case it can go in. Come with 2 batteries. I don't know if it needs 2 and there's just a spare, but apparently this is what the screwdriver is for. Okay, looks like it just takes one battery. That's kind of nice to come with spare then. Of course, the screw is tiny. It's kind of convenient to come with a screwdriver though. I like that. Okay, so let's turn it on here. How do you on it? Does it come on automatically? No. Okay, we're going to have to look at the manual here. Oh, you can't make this stuff up. You can't. Put a CR2032 battery and plus should face outside. Close the battery door with a screwdriver. Long press mode button to turn on the anemometer. If it is not turned on, please repeat the step 3. Install the protective cover and lanyard. Oh. 1. Remove the rubber protective case. Open the battery cover with a screwdriver, using a knife or tweezers to push the iron piece forward to ensure better battery contact. So is this implying that the reason it's not turning on is because the battery tab is not? No, let's do a long press of the mode. I don't know how long a long press is, but I think we've probably got there by now. So that means we're going to have to use a knife or tweezers to pull that tab out. Yeah, it fit in there really tight. I find it hard to believe that that's the problem, but and this isn't a knife or tweezers. Hopefully this still works, but let's see. Well, I think that just broke. Oh boy, we are not off to a good start here. Well, it's certainly pulled out now. Oh, is this one not pulled out enough? I'm going to break the side contact too. Oh, there we go. Now we're getting something on here. Okay, well, lo and behold, it just needed what it said in the manual. I think that's something. Okay, let's long press again. And now we have the anemometer is working. So we need to change this to feet per minute. There's feet per minute. Nice and warm in here. Okay. Better put it in the protective cover before it breaks, as this thing does not seem very durable at all. All right. So let's see here. So let's turn this fan on. Did I plug it in? No. It would have made a little too much sense to plug it in prior to the video. So let's see here. How many feet per minute does this output? I'm going to check it in miles per hour first, just for my own curiosity, because I don't know what the heck feet per minute is. I can't relate to that. There we go, miles per hour. So, you can't see it. So this says it's about 21 right there. And if I go a little closer, there's 22. I think 22 is the strongest that we're going to get. It's just very sensitive to the orientation in which I hold it. Huh, I guess it is stronger on the right side. That's almost 23, and that's only 20, and that's 21, so maybe we'll say 22. See, that's the problem I anticipate with the ceiling fan, is that it's gonna be inconsistent. Well, I just remember we need stupid feet per minute, so that measurement I just took was of no value. Oh, this is a big messy number here. That's about 2,000. About 1950. And that's about 1750 over there, so maybe we'll go with the 1900. Yeah, we'll go with that. So we'll say 1900 for the stupid feet per minute. Let me get a new piece of paper so we don't contaminate the one with the formulas on it. Okay, so this is 1900 stupid feet per minute. And now we got to measure the surface area of the output. You know, which, I mean, even this is not super precise because there's thickness here that's being taken up by the guard. We'll say this is about 6.5 by 2.75. And now this is just getting, it's a really messy calculation because now we got to move this odd number of square inches to stupid square feet. I hate inches and feet. They're stupid and dumb. So 6.5 times 2.75 equals 17,875. Now, how do we put that? We got to put that. What is the formula to take square feet to square inches? Oh, I hate these. They're so stupid. If it was meters to centimeters, it's so simple. We would have to put. What the heck? How do we find out? What is it? 12 divided by 6.5? Is that how you convert it? No. 12 times 6.5. I don't even know how to convert stupid inches to to feet. It's got to be, I thought it's 6.5 divided by 12. I hate this stupid inches and feet trash so much. Okay, yeah, that's what it is. It's divided by 12. Stupid, it should be divided by 10. So it's really 0.542 times 2.75 divided by stupid 12 equals, nope, I typed it in wrong. 2.75 divided by 12 equals 0.23. So now 0.23 times 0.542 equals it's really only 0.12 square feet. I guess that's about right. Okay, so then we know the area, so the CFM equals the area, which is 0.125 times the velocity in feet per minute, which we said was 1900. So 0.125 times 1900 equals 237. So the manufacturer claims this moves 300 CFM, and this calculation says it moves 237.5 CFM. So, I mean, it's not totally off. It's in a ballpark. The fan is dirty. You know, could it move more air if it was clean? Perhaps. Let's see, if we did 0.125 times, I think we said the highest was like 2200. That's 275. So let me go back here and take the highest number I can possibly get out of this. Like 2068, I think, was the highest. Now, see, the thing is, if you come back here, now all of a sudden the airstream is wider. So where is it measured? I don't even know. Yeah, about 2,000 is the highest I can get, and then over here it's only about 17, 18. Let's see what it is on low. 1,182. 1,182 times 0.125. On low, it moves 147 CFM according to these calculations. I don't know. I guess the next thing to do is to deal with a ceiling fan. And that becomes even more complicated because now it's a circle. So this is for the blue blower. And we'll say the low was 147.75. Okay, so now for a ceiling fan, we have to calculate, if it's a 52-inch ceiling fan, it's going to be was it radius times pi squared or something like that? But now we got to do 52 divided by stupid 12 gives us stupid 4.3. So a 52-inch ceiling fan is really a 4.34 foot fan. And then if we divide that by 2, the radius is 2.167. And 3.14 times 2.167 is 6.8. So we'll say the surface area of the ceiling fan, the area equals 6.8, but that's not including the inside of where the motor is. So I'm just going to measure this fan, and we're going to say that the like the area where the irons is, I'm going to call that about 15 inches. So now we got to do a 15 divided by stupid 12, 1.25. So let's take 6, so we're going to minus 1.25, and so 6.8 minus 1.25 equals 5.5. So I'm going to use 5.5. So for this one, I'm going to say that the area of a 52-inch fan equals 5.5 stupid square, stupid feet. Hate inches and feet. So now let's take a look at the fan. And let's see how much air does this fan push. It's not even pushing enough air for this to barely register. I'm going to put it on high. I'm not surprised. This is not a very powerful fan at all. This one is more for aesthetics. Now let me come up close here, and that's about that's 300 and about 350 on the end. It's about 300 right there in the middle. And then in here it's only about 200, and there's nothing detectable by the irons. The meter's not even spinning yet. Still not spinning. Okay, it just starts to spin right there. So that was kind of what I observed, just from feeling it. There really isn't much going on past right around here. If the meter has a running start, it'll register 200 there, 192, 182, 170. It's kind of slowing down. So on the outside, 346 is the highest I saw there. We'll go 346 is the highest, and 173. So 173 in the middle and 346 on the outside. So it's like a gradual change as you move to the inside versus the outside of the blade. So I wonder if we should maybe take an average here. I think that probably makes the most sense. So let's do 346 plus 173. That equals 519. And we'll cut that in half for 259. So we're going to say the speed of this is 259.5. I mean, this number is so big, the decimal's not really making a big difference, but 259.5 feet per minute. So that makes our formula, the area, which is 5.5 times 259 is 1,424. That's not very much airflow at all. 1,424. That is quite pitiful. Let's excuse me, I'm recovering from a cold. Let's go measure a different ceiling fan that is a little bit more powerful. This ceiling fan is a lot more powerful. So let's get a measurement on this one here. I'll put it up to high. This is 443 was the highest number on there. And the airflow pretty much just cuts off. It's not even reading anywhere past halfway in, which would make sense because this is much higher up to the ceiling. It's not going to do anything in the middle here. I don't really feel anything until right around here or so, which is kind of the same with the other one though. So this one, kind of like a gusty, inconsistent breeze. And I think 446, I think we said, is the highest I was able to get here. 423, I saw a couple times. Yeah, 423 again, I've got that steady. All right, we'll go with 423 for this. And this is like, it's 182 right there, so we'll go with 182 and 423. That's 302. That's 1,661, which is more, but it's not much more. So these numbers are very low. Now, I don't know, we've talked about these CFM calculations in the past and how I really don't give them much of any credibility whatsoever. And part of the problem here is that we don't know how these manufacturers are measuring the CFM. Does the manufacturer account for the center area where it's not moving any air? I don't know. Does the manufacturer measure the airstream right up against the blades, or does it measure it a couple feet away from the fan where the air is starting to disperse and there's, the perception of a wider surface area from the air pushing around the sides? I have no idea. These calculations, it's the basic formula. I mean, I feel like that should be fairly accurate, with the only discrepancy being I don't know how, how do you, because the airflow is not the same through the entire depth, the width of the blade. When you move to the outside of the fan, it's stronger. When you move to the inside of the fan, it's weaker. How do you come with that number? I feel like an average is a pretty reasonable measurement. And this fan is really quite weak. Compared to the force at which the blue blower fan pushed air, and that calculation was in the ballpark, and that calculation wasn't just totally bogus. I don't know. I've always kind of felt like the CFM ratings on these ceiling fans were just totally off the charts, and this kind of confirms that. So I don't know. That's my findings. I think that the CFM ratings provided by the manufacturer are totally bogus and ridiculously inflated. Very curious to hear feedback in the comments box if anybody has any experience with trying to calculate this, any input on what should be done differently, etc.